Hi, I'm making this video to address some misconceptions I came across on the internet, and I find it important to clarify matters. So here we see the first, I read this here, uh, that the ferrolens senses somehow the magnetic vector potential A, which is defined by this Maxwell here equation. The curl of the potential magnetic vector potential A of the field is the magnetic field intensity B, and therefore displays equipotential lines of the field of a magnet. Well, this is not true. The above suggestion is wrong because a potential is not a physical property and phenomenon, but a mathematical attribute we assign to a field. You cannot display potential with a physical sensor like the ferrolens or any other physical sensor which operates under physical rules and laws. Well, you see, even in the case, say we have a classic voltmeter, which is measuring potential difference, yes, on a circuit. Even this, although this voltmeter operates on physical laws by having an electrical coil which is deflected inside the magnetic field by the Lorentz force, the problem is that it's not 100% physical like the ferrolens, where it has magnetic nanoparticles inside. We assigned the declination of the voltmeter, of the needle of the voltmeter, the declination of this needle by the Lorentz force to a scale. So there's algorithmic processing involved now here. It's not a pure physical device. So we have this scale calculated by experimentation and also by applying mathematical rules. So it's a hybrid device, not purely operating by physical laws, which is the Lorentz force, but also by algorithmic processing. But a physical sensor, like for example iron fillings, which for the plotting the magnetic field, magnetic force lines, and also the ferrolens, has no such algorithmic processing. It's a pure physical device, and physical devices can sense only force and motion. These are the only phenomena of electromagnetism. There is always force and motion. Potential is an attribute, a mathematical attribute we assign to a field to characterize it, but it's not a physical phenomenon. So also magnetic dipoles of a permanent magnets, in contrast to electric dipoles, are not monopole charges. Therefore have a non-zero curl in total field, and therefore cannot have an equipotential plot of the field assigned to. So first we have to understand what is an equipotential plot of a field, which is a man-made plot. It's not a physical entity. So we have here two electrical charges, a positive charge and a negative charge. These are monopole fields, and we see the only physical existing lines in such a field are these red lines, which is the force vectors, the electric force vectors of the field. These circles here are man-made plotted, and we assign each point on the circle is there where the force vector, the electric force vector, has the same value. Yes, but this gray here circles are not existing in the field. It's just a mathematical derivation. You just see, from the inverse square with distance rule, the the force will fall, the electric force vector will fall with the square of the distance. So all the points here, because it's a monopole charge, they have all the same value, the force vectors. And this we say it's an equipotential, but it's not physically existing on the field. It's just a mathematical attribute we assigned. So it's impossible for a physical device like the ferrolens to show by definition magnetic potential and even more equipotentials. Okay. Now we compare. Now we clarified what an equipotential plot means, and it applies only to monopole charges fields. You see now we compare an electric dipole field with a magnetic dipole. First, we have to clarify that there are no magnetic monopoles in nature, at least they are not found yet by science. So you cannot treat this here, this configuration of the two monopole electric charges, the same as a magnetic dipole. A magnetic dipole, you better imagine it as one entity. Forget about these are not two separate discrete entities, north and south. It's just one entity. So here we say about the electric dipole here that it has zero curl. Zero curl is a very difficult definition to grasp, but it basically refers that if you have here a monopole charge, the force, the line force here, the electric line force, derivates and goes away to infinity and never returns back to the charge. So this means zero curl. So we have here the two charges with the equipotential plots, which I again repeat are mathematical attributes we calculate for the field and not physically existing on the field. The only physical existing are these vectors here, the force vectors. So this is the isopotential plot for the one charge, and this is for the other. But this here, as many wrongly assume, has nothing to do with a magnetic dipole. In a magnetic dipole, we have the totally reverse situation, meaning that the field has non-zero curl. So what that means? It means that it has curl. Non-zero curl means that it has curl. In contrast to the electric dipole, which has zero curl. Meaning, here in the magnetic dipole, all the magnetic force lines, or called also magnetic flux lines, or just magnetic flux, they're returning from the dipole, starting here, and return back to the dipole, starting from the North Pole and returning to the South Pole. Again, don't mix up, don't treat it like an electric dipole. These are two monopole charges. The electric dipole consists of two monopole charges, and but a magnetic dipole consists is just a magnetic dipole. It doesn't consist from separate magnetic charges, because they are not found in nature. There are no magnetic monopole charges found in nature. So this here also has zero curl, and this here has non-zero curl. Therefore, because a magnetic field has a non-zero curl field, it cannot have equipotential lines. Okay, and here, just to clarify, here it doesn't mean that at this point here the field strength is the same as this point here. These are just the discrete separate equipotentials of each charge plots, and of course here the field is much different, the value of the strength of the field here than it is here. Just a representation. Yeah. So how is possible then something which cannot exist to be displayed by the ferrolens? You see what the misconception here is. So summarizing, the only physical existing lines in magnetic field inside and outside the magnet are the magnetic force lines, or else called magnetic flux, picked up and displayed by the ferrolens or any other physical magnetic sensor, like the, for example, iron fillings experiment. Physical sensors can only sense force and motion. Thus, in our case of the ferrolens, the magnetic lines of force, or else called magnetic flux. And this has been proven many times, and you will later, you will see later in this presentation a simple example experiment you can do yourself to see that this is true, and the ferrolens displays the only thing which consists a magnetic field, the magnetic lines of force or magnetic flux. I can see the confusion. The confusion comes because the field we see by the ferrolens does not match what we were taught in schools. But I have proven with my publications what really happened. The really confusion, the source of the confusion, comes from the next misconception, which says here, the ferrolens displays the magnetic field existing outside a magnet. So this is natural to get confused, because you think that what you see on the ferrolens is actually the outside field of a magnet, but it's not. This statement is false. The ferrolens is a quantum nanoparticle-sized magnetic flux viewer, and have 3 publications on this matter made. And it displays not the coherent outside classical north-south field we are taught in schools of a magnet, as in the case shown by iron fillings, this kind of classical field, but instead, this is the key point, the inside quantum magnet field, yes, which is also by literature is different. The inside field of a magnet is different than the outside classical field. So imagine imagine the magnet as a generator. It has an inside field and it produces an outside energy flow. We call the classical north-south field. Yes. But what the ferrolens is actually doing, it zooms in the magnet material and projects its inside net quantum dipole vortex fields, and we'll show it in. I'm sure most of the ferrolens enthusiasts know what I'm talking about this dipole vortex field, which has a vanishing curl, a spiraling dipole field of magnetic flux lines. And it projects this inside field, it projects it to the outside, which is of course different from the classical macroscopic field we are all used of. So let's now see what are the meanings of these words. So you see here the classical field, which we can an imprint of it we can achieve by using a simple iron fillings experiment. And here is the field we see inside the magnet with the ferrolens, the quantum field. Of course, why it's quantum called? Because it is sensed by nanosized particles. The particle size, the discrete particle size is 10 nanometers. So this is the quantum field of the magnet. And we see here that it consists from two dipole vortexes, two vortices which are back to back. This is the domain wall, or it's called, enthusiasts are calling it block domain wall, but there are reasons now not to call it that way. But just stick now, it's not, just stick with the domain wall, yes? So, because block domain wall refers to something different. it's the inside. If you have a ferromagnetic material, the domains inside, little chunks of metal, they are randomly polarized, and the boundaries with other chunks of metal. We refer this region, this intermediate region, as block domain wall. But in classical electromagnetism, a magnet has no domain wall. But we have proven with the ferrolens that there is a domain wall, but let's not call it now block domain wall, just a domain wall. It's actually the joining point of these two counter-rotating, counter-geometrical shaped rotating vortices, which we can see here with these thick colored lines. Thick colored lines. And to show what is going on here, we have overlaid the iron fillings pattern with this little brown here lines with a quantum field shown with ferrolens. So what is now the mechanism? These two vortices, these two dipole vortices, are generating to the outside of the magnet the classical field, which is depicted here with the iron fillings and also here overlaid with these little brown lines. So imagine it like inside the magnet, there are two fans, yeah, counter-rotating, and they produce this flow of energy, this flow of air in accordingly, which is the classical field, called classical field, and the inside field is the quantum field, which is sensed by the ferrolens. And a more simple illustration of this very important observation we get with the ferrolens, which I must say is a groundbreaking observation of how magnetism works in ferromagnetic materials. You see here the two spirals here, which are counter geometrical vortices, are in each pole of the magnet correspondingly, and these two consist the inside quantum dipole vortex field of the magnet, which these two fans now generating the classical field of the magnet on the outside. So we get the classical field, the macroscopic cold field, from the outside of the magnet, and inside the magnet we have its quantum field, which consists of this dipole vortex configuration. Yes? So coming back now about the ferrolens showing really magnetic lines of force, or else called magnetic flux and nothing else. There's a simple experiment we can do that conclusively proves once and for all that the ferrolens shows magnetic flux lines, but with the only difference that it does not show the field, the magnetic flux lines of the field outside the magnet, but the quantum field inside the magnet, and it projects it to the outside. It zooms in and then projects it to the outside. And I understand your astonishment, because you see the field outside the magnet, the boundary of the magnet, the magnet body, and everyone can logically think, nah, that's the outside field. But no, there are some experiments we can do, and I will do in the future, and that also conclusively prove that what we see is the inside field of the magnet zoomed in and projected to the outside with the ferrolens. So we see here a ring magnet, and we see with the ferrolens its magnetic field on the pole. The ring magnet, the face of the ring magnet here, touching the ferrolens, is projecting its inside field on the ferrolens, and the field now is displayed. We can see it's clearly a vortex torus. Also, another important realization about the ferrolens that it's magnetically see-through. You can see through when you see here the pole. here, the field, it's actually the both poles of the magnets project their fields on the ferrolens surface. So you see through both poles here, thus the total field of the magnet, which is a torus. And we see here how they're spiraling in here to the center, each line here. Yes. And also the ring magnet has a unique property, a unique characteristic, that is the only type of magnet which can confine its field inside its air cap. So you get the total field view inside its hole here. The hole here, inside the hole, you can see its total field. So this is the field of a ferromagnet, yes, of a permanent ferromagnet, which, as we say, is its quantum field, and it consists of this dipole vortex configuration. So now we go to another type of magnetic field, which doesn't involve any ferromagnetic material. This is an air coil, meaning that there is no inserted ferromagnetic core, which whenever we insert here ferromagnetic core, then this coil is not an electrical coil, it's called an electromagnet. And in this configuration, as theory also predicts, the field lines, the magnetic lines of force or magnetic flux is straightforward. They are very straight and very homogeneous. And surprisingly, but not really, we see here this also when we view the magnetic field of an air-capped solenoid with a ferrolens. This is actually an experiment made by Brian Kerr, credits to him, and I will link his source video, on the description. Yeah, so you can find it. So we see here the lines. They're very going here. We see again as I said, the see-through property of the ferrolens. We can see both poles of the magnet actually. So it's like looking from here and watching over the other hole here. So you can see through the whole length inside the coil, and actually with holographic depth, which is astonishing. So you see here the lines are going straight in, as predicted also by theory. So now we definitely know that the ferrolens shows magnetic lines of force, or else magnetic flux, and nothing more, unless somebody is suggesting that here, when we put a ferromagnet magnet, it shows magnetic potentially, magnetic potential as assumed, which I proved that this is wrong, the statement is wrong. And then magically, when we switch to an air cap coil, it magically converts, and now it shows magnetic flux. So that's actually an impossibility. So yes, continuing. Yes, I like now something to comment about the very good program of, and it's a unique program from Michael Snyder, the Big to Mac, which I recommend to everyone to use. It's the only program which can simulate closely enough, and sometimes exceptionally good, what we see. It can simulate what we see with the ferrolens. It's a ferrolens simulator. Just put the magnet, you describe the magnet and input it to the simulation program, and then it outputs what we will see if you had a ferrolens. But there are some very important points we have to notice about this program, and what are the differences of this program with what we actually see on the ferrolens. There are some differences, and I have to point them out. So we know what I say now. It's with the ferrolens operated with an LED ring, because we will see later there's a difference also when we operated with a single LED on the center under the ferrolens, on the center of the ferrolens, which is, I call it the cloud mode of operation. So now, what I said in the next two slides, what I say is about the next one slide, actually, is about the ferrolens when operated with the LED ring on the perimeter. Yeah. Okay. So here we have a dipole magnet on its side put on a ferrolens, and here is what the output of bit to Mac program will produce. In first glance they seem very similar, but let's have a more closer look. You see here that the lines produced by the simulation program from Snyder are more or less concentric circles. Yes? But here, which is the actual display of the dipole magnet on the ferrolens, this is not actually the case. You see here, you remember I've said that these are vortices, and vortices are spiraling in. So they have a vanishing curl. This is also called a vanishing curl. Yes? So we see here the lines of force are actually spiraling in. There are no concentric lines. Here they're spiraling in. If you watch closer the trajectory, you will see that this is here the case. Yes, and this is more evident here where the bit to Mac simulation program displays the field on one pole of the magnet. So just put one pole of the magnet above the ferrolens, and this is the actual display of the ferrolens. So now it's even more evident. You see they are spiraling. The lines here are spiraling in. They are not concentric, as shown by the simulation program. In actual fact, they are not stopping here. They're going all the way spiraling here in the center of the black hole. Why we don't see that? Because the ferrolens shows the poles like two black regions, black circles, and there is actually an explanation about that. As you go in here, that center, the magnetic flux density B, the B field, is very strong. So they are very dense. The density of the lines are here very close. Each line becomes very close to each other. And there is a phenomenon, it's called light extinction due extreme scattering. So if you have an extreme scattering, the light gets bounced on and off very rapidly and in very close range, and it becomes extinct. So it loses its energy and becomes extinct. Therefore, we have this. The ferrolens shows this center of the pole here as a black region. But in reality, if you see the trajectories here of the lines are going in here and spiraling all the way to the center, like here in this illustration. Yes? So this now is a big difference. It's a huge difference. When the LED, I repeat, is operated as with an LED ring on the perimeter, yes? However, again, Big to Mac is excellent. It's an excellent program when we have a magnetic array. So when you have many magnets in an array configuration which are interacting the one with the other. In this case, what we see on the simulation is actually very close to what we have with the actual view on the ferrolens, because the interaction of the magnets, the curl of the magnets are become less and less. They are becoming more straight lines, and therefore, actually, the simulation matches with what we see on the ferrolens. However, an experienced eye, trained eye, can see the difference in the curl of the magnetic force lines between the actual display from the ferrolens and the simulation. Yes, but again, I see for magnetic arrays what we get with Big to Mac simulation program is very close enough uh, from the actual field shown by ferrolens. Where the Big2Mac program excels and is very good is in the case we operate the ferrolens in cloud mode, as I call it. So in cloud mode, you don't have an LED ring around. You have just a LED at the center, dead center of the ferrolens. And in this mode, we cannot see individual discrete magnetic flux lines. We see just only a shell of the field of the magnet, a shell of the magnetic flux lines, the perimeter of the field. And this actually is a very good infers very good to something we call in electromagnetism the not the magnetic vector potential, but it's called the magnetic edge field potential, or else the static potential of the field. Yes. So we see here Big2Mac simulation simulates correctly the display of the ferrolens when the lens is operated with a single light source at the center, cloud mode of operation. In this mode, the operation of the ferrolens, the outline geometry shells of the magnetic field is displayed and not the discrete vertexing magnetic flux lines. The outlines of the magnetic edge field is in this case displayed and also simulated in the software infers to the magnetic scalar potential, yes, the static potential, and not its magnetic vector potential. You can, if you want to look it up, you can see here to go to wiki, just type in magnetic potential, and there's a subsection of the article which is called magnetic scalar potential, and they have actually a similar graph, but because you cannot, a scalar potential is not a vector potential, and you cannot plot it with lines. They use colors. So you use a red color, and as you go farther away from the magnet, the red color becomes lighter, and then they use, I think, blue color for the south pole. But again, this cloud pattern we see, which is the perimeter, the shell of the magnetic flux field of the magnet, it's very good analogy to the scalar or else static magnetic potential of the field. And there we have actually a perfect match of the simulation of Schneider's Big2Mac software with what we actually see with ferrolens. So again, the program is the only, it's unique and priceless, the program of Schneider, and I suggest everyone to get this program and have fun and do some serious work as well. Especially when we have, which is usually actually the case, only theoreticians are playing just with simple magnetic dipoles. Usually when we have to do engineering work, you make magnetic arrays, and it's very good in displaying that. And also when we operate in cloud mode and we want to see the static, the cloud pattern field of a magnet, then this Big2Mac simulation program does an excellent job. So let's continue. Last but not least, the last misconception I want to address, which I came across on the internet, is that the ferrolens for displaying the magnetic flux lines of the field operates as a diffraction grating for light. Well, if you look at what diffraction grating is and what actually diffraction means, light diffraction, you have a slit or an edge, like a needle, the tip of the needle. And if this insides is close, very close, or the same as the wavelength, which is hitting this slit or passing through the slit or hitting the edge of a needle, for example, if it's the sides are matching or a bit smaller, but be careful, a bit smaller or the same sides, then we have the diffraction effect, which is an effect where we have light frequency dispersion. So, and it produces always, when referring to visible light, a rainbow effect. You can see that more in a bubble. When you have a soap bubble, you get this, this rainbow colors. We can see someone in a bubble. Yes, this is called diffraction. But when you study we see also visible light. The lines we see on the ferrolens are visible colors. Yes, about orange and some other colors, but there are hundreds of nanometers. They are more than 250. Yes, 250 nanometers is in the boundary of ultraviolet, the upper boundary. Yes, but orange is more like 250 nanometers, more on the range of 300 and 400 nanometers. So it cannot be diffraction. It cannot be operating. The ferrolens is not operating like a diffraction grating, because the sizes we have, yes, we have sizes on the type of 50 nanometers. Remember, each discrete nanoparticle is 10 nanometers or less, but the form of course chains, but these chains are not that big. And remember, it doesn't matter the chain. It means the tip of the chain is the important factor. So it's not the length of the chain of the nanochain, it's the thickness of the nanochain. And the thickness of the nanochain is not more than 20, 30 nanometers. So you have, you cannot have diffraction, because there is a large difference between the wavelength, which is 300, 400 nanometers, and the thickness of the needle, which is not more than 20, 30 nanometers. But this is actually the perfect conditions for another phenomenon, light phenomenon, which is called light scattering. It's the phenomenon that produces the blue sky. So when the particles are much smaller than the wavelength, then we have light scattering. And this is actually the case, and I will now prove it, the case how the ferrolens works, in my opinion. The ferrolens is a magnetically controlled light scatterer. That's it. The ferrolens is a magnetically controlled light scatterer. Means whatever magnet we put in, the magnetic lines will match and align to the direction of its quantum inside field, and the light will then scatter it and produce the magnetic lines of force we see on the net, on the magnet, yes, on the ferrolens. That's the way these field lines are made visible, by scattering, not by diffraction. Remember, diffraction produce only a rainbow effect. Okay. So now we see here an example, which again goes to Brian Kerr. I linked here his source video. You can go in. So this, what is this? This is a CD-ROM, which has, very fine. The data are imprinted like just fine dots. This formation of its surface, not visible with the eye. And this is now actually what we call a diffraction grating. The surface of a CD-ROM is a diffraction grating, and what Brian Kerr did, he put the LED ring, and a white LED ring we use also on the ferrolens, on the perimeter of this CD-ROM. And you can see here the rainbow effect. This here is because we have light frequency dispersion, like a prism, a prism, and you get this rainbow effect. There's no magnetism here, yes? It's just only diffraction. You can see here, let's have a look on part of his video. Yummy. Okay, you have here the rainbow effect. So this is normal diffraction produced by diffraction grating, like a CD-ROM. Okay, so continuing. So I believe that's the case. And why? Because now here we see the actual display from a ferrolens, and why a white LED is used on the perimeter of the ferrolens, and we get this characteristic orange color lines by the ferrolens when a magnet is placed, yeah, of the field of the magnet. So we can see here the color of the, remember this is white light, yes, this is white light LED. So you know white light disperses to all the rainbow colors. If it was a diffraction grating, we would definitely see a rainbow effect. But instead we see here the color is very uniform orange. Okay, you have a different tone, a different brightness here, but in general the color is very uniform orange, and there are no other color present. So that means that there is no frequency dispersion taking place here, and therefore I believe this is not a diffraction effect. The lines are not because the ferrolens is behaving like a diffraction grating, but it's, as I said before, it's actually a magnetically controlled light scatterer. And what controls this light scatterer is the magnetic force lines of the magnet placed on top or below the ferrolens. Okay, and okay, again this here the conclusion, my conclusion, in my opinion, again, the ferrolens does not behave as a diffraction grating since there is no visible frequency light dispersion and rainbow effect, but instead as a magnetically controlled light scatterer mechanism displaying the magnetic force lines, or else magnetic flux, inside a permanent magnet, thus the quantum magnet field of permanent magnets. So that's it. That was the presentation, and yeah, I have nothing more to. I believe that this video can be useful to clarify some misconceptions, and I thought it was important to do because what matters is the progression of science. That's the end result we all want, and to find out the truth about how nature works. And the ferrolens was, I believe, is a wonder tool to decipher magnetism, which is, as many believe, and it's true, is not completely understood yet. And there will be surprising if we understand magnetism. Who knows, maybe we can decipher something else we totally don't understand yet as a concept and a cause, which is gravity. But this I will keep it, I reserve it for another presentation. So bye for now, thank you very much. This is Emmanuel Markoulakis signing out. Bye.